Welcome back. Another video, another day, another dollar. Thank you. Shout out GitHub followers. I see all y'all. Really appreciate y'all. Gotta make the Pokemon sound of the day. Today we have Clefairy. Let's take a listen, shall we? Clefairy, Clefairy. Yep, that was Clefairy right there. I'm not gonna lie, guys. I played some poker last night and lost all my money. And by all my money, I mean $10. Yeah, I'm a little out of it today. I don't know if you guys can tell. Maybe not. If you guys couldn't tell, you guys are about to be able to tell. We're going to start off with one Leetcode today, and then I'm going to do some project work, only about an hour. I have a midterm tomorrow, but it's like for a fake class, so it shouldn't be that hard. Longest square streak. Okay, let's try this one. This looks like a regular ass problem. Alright, you are given an integer array of nums. Wait, after sorting the subsequence, each element except the first element is the square of the previous number. Choose the subsequence. 4, 16, 2. It can be shown that every subsequence of length 4 Okay, I have an idea. So I'm gonna hash. All right. So here's how I'm gonna think about it, right? I'm gonna hash this. Dude, I'm so low energy right now. Oh my god. Dude, okay. I'm a little bit hungover, as they say. So bear with me. Damn. So I'm gonna hash this whole thing, put it in a set, maybe. Yeah. And then what I'm going to do, because the subsequence is, you can just choose any of them, right? Yeah, so I put these in okay, for the fourth time, I put these in a set. And let's say I'm going to start at like 4. I'm going to check, is 4 squared in here? Oh, it is. Okay, so it's 1. That's the current max. Okay, is 4, oh, and then we go to 2 to 4 to 16. So then it is 16 squared in here? No. So then we know it's, okay, let's just do that. Okay, 4 num. Okay. I think I can do this hash equals set num for num in nums. Is that how that works? Two, 3. Yeah, okay. For num in nums. X equals num. We're gonna have a res equal to 0 or negative. Yeah. X equals num. Okay, and then it's while X in hashy. So it's in there right now. Hold on. So it should be -1. And the counter is -1. Counter plus equals 1, x two. Wait. X equals x times to the second power. And then is that it? No. How is it 3? Oh, it is 0. Yeah. Oh, so 1 cannot be 1 then. Is it like that then? This is not a medium problem, dog. This is easy as hell. Am I tripping? Or did I do it wrong? Six lines with hash map. Without sort. Dynamic programming, bro. What? Oh my. Binary search. Beats 37. Is mine bad? What is that? Wait, how are you supposed to do this problem? No, see, his is O of n, like a pure O of n. Oh no, but it's n log n. Can I do an analysis on mine? I'm actually really curious what the Leetcode thing says. How do you do it? Come on, I get one free oh, there it is. Okay. All right, let's just try to do it. Let's try to run through it first and then see what it says. I feel like mine is also n log n. Because obviously I have the O of n, this one, and this one. We can ignore this though. This is O of n, this is O of n, this is the same thing, right? But once you get to here, you're doing this operation, which, like, while x in hashy, you're gonna, since you're multiplying by 2 exponentially, that means you're like exponentially running out of numbers. Like you're, dude, how would I explain this in an interview? Like, this is kind of difficult. Okay, like for when it's linear, you're checking every single number a single time, right? But when you're doing this exponential, x squared, you're checking, you're skipping a lot of numbers with each check. And each time this loop runs, you're skipping double the amount of numbers. like for example, like when you go to 2 to 4 to 16, right? There's the difference between 2 and 4 is only 2, but the difference between 16 and 4 is 8. Wait. No, it's 12. Unreal math. It's 12, right? So you're running out of numbers that could be in the hash map quicker and quicker with each iteration. That's why it's n log n. I could just be wrong, but I like convince myself it's n log n. Okay, it's not. Oh, man, dog. Using set. I wonder if people did what I did. Yeah, right here. Literally the exact code I had. So you can just do this. I didn't know that. Oh, by the way, my streak. I fucking hate Leetcode, bro. I'm technically, like, obviously I haven't missed a day, but since it's past 5 p.m. or whenever the Leetcode resets, I miss a day on Leetcode. That's so boring, dude. What? Why does it do that? Can I set my time zone on Leetcode? I don't know if there's like private info on this thing. Sorry, I know I'm wasting a little bit of time right now. Okay, well, I just put my location as Chicago. I don't know if that did anything, but United States, awesome. Okay. Man, we can do one more, dude. That was way too easy. For real. Hold on. Sorry, guys. I'm so distracted right now. But that's just how it be sometimes after you drink too much of alcohol or whatever I did. Okay. Let's do another one. Let's do a... Yeah. You know what I kind of want to do? Is I kind of want to try this. But I have no idea how. Like, I think I might just go straight into the Leetcode video on this one.
Hey.
Oh my god. Just because, like, I understand what a try is, but I have no idea how to, like... I'm pretty sure a try, though, is, like, I don't know if I'm wasting my time trying to do this myself before I watch the video. But I'm pretty sure it's just, like, an array of an array. Like, if you have, like... If you're inserting dog, right? Like, you have, like, all the letters, like, A to Z, right? right, to Z, in like the first phase of the problem, because you're only looking at the first letter. This is like assuming you kind of already know what a try is. I'm just trying to explain how I think it's implemented before I cheat and look at Leetcode's thing. But like for dog, like here would be A, right? Like this is an array for A, or like the first letter of A. And then you go here, and this is B, right? C. And then this D is going to have like 1 or some it's going to have another thing in it. Something like that. It's like nested. I don't know, but they're like nested like infinitely. I don't really know how to make it. Like, I don't even know what I'm initializing. Or is it a set of a set of a set? But how do you keep track of them being connected? No, I'm just looking at Nico's video. I'm not trying to sit here and figure it out.
Hey,
that was kind of my plan from the start, but...
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve implement try, aka a prefix tree. So a try or a prefix tree is a special type of tree, and it's used to efficiently store strings. And the applications are some stuff like autocomplete and spell checker. The reason is because the prefix tree allows you to efficiently filter and search based on prefixes. So let's look at the actual implementation of it. So we're going to have a object. That's what we're going to be doing this time, a try object. And our job is to fill in
No, it's just a set of a set of a set. Or is it? I don't know.
The first function is going to be inserting a word into the try. The second function is going to be searching for a word in the try to see if the word exists. And the third function is going to be to check if there is a word that starts with a given prefix. So those are the three functions we're going to do. And let me just go through the rest of this explanation, and then I'll show you what a try actually is. So here you can see basically what we're going to actually be doing. They're going to be instantiating the try, right? We're going to be inserting a word such as apple, right? Then we're going to run search. Does the word apple exist? Well, we just added it. So of course we're going to return true. Apple exists. Then we're going to check, does the word app exist? It does not. The word app does not exist. And third, we're going to try starts with app. Are there any words that start with app? And answer is yes, so we return true. Remember, apple starts with app, so we return true. The prefix, right? This is the prefix. App is the prefix of apple. So now let me show you the actual data structure. So let me show you what a try is, and in this problem, they told us that the limitation is that the words are going to only have characters from lowercase a to z, right? So this is lowercase a to z, so that means we're going to have exactly 26 characters to worry about, right? But so this is a tree, right? It's a prefix tree. It's a special kind of tree. So initially, our tree is going to be empty, right? But let's say we want to insert apple. So if we want to insert the word apple, how can we do that? Well, this is what we're going to do. We're going to create a node for the lowercase letter a, right? Then we're going to create another node for the lowercase letter p. And we're going to basically keep doing this for every character in the word that we're inserting, right? We're going to say A, insert it, P, insert it, second P, keep doing that. And every time we're inserting a new character, we're going to add it as a child of the previous character. So we inserted the word apple, right? We can clearly see that. One more thing we have to do to say that this is the word that we inserted is we have to mark the end of the word, right? So this is the end of the word, right? The letter E is the end of the word. So we're going to mark it such that so that this is identified as the end of the word, right? Not, for example, this, right? If we mark this as the end of the word, then we're basically saying we inserted the word AP. But we know we actually did apple, right? Full on apple. This is the last character. So we mark here as the last character. We are marking it, even though it's kind of self-explanatory because this character E does not have any children. It's basically obvious that this is the end of the word, but we're still marking it just to be safe. So you can kind of see what we're doing here now, right? This is kind of the root, right? So really what's going to be possible is we have 26 characters, right? So potentially we could have a node at the first layer for every character, right? So A, B, C, D, etc., right? We could have a node for each of these, basically indicating that here is where we're going to put all of the words that start with a B. Here we're going to put all the words that start with a C. Here's where we're going to put all the words starting with D. So the next thing we're going to do is run search. We're searching for the word apple. So how are we going to do that? Well, we're going to start here at our root, right? This is technically our root, even though it doesn't really have a character, right? So that's basically just a placeholder node, right? It doesn't have any characters, but it's considered the root, right? And so we're going to check, does this root have the child of the first character that we're looking for, right? So take a look. This is the word we're looking for. Obviously, we're looking for the character A. So we check. Hey, there's the A, lowercase a, right? It's the first character of the word. That's what we're looking for. Great. Now, for this A, we're looking for the next character, right? So does this A have a child P character? It has exactly that. So we do have this P, right? And this is what we're doing, right? We're going character by character in the word we're searching for and checking if a node exists for each character consecutively, right? As a child. So next character, P. Does this have a child P? Yes, it does. Next character, L. We have a child L. Next character, E. This is the last character, so we do have an E over here, right? And last thing that we have to confirm is, okay, this is the last character. Is it marked such that this is the end of the word? Is it marked as if it was the end of the word? It's blue, right? That's what we're doing to indicate that it's the end of the word. So it is, right? So clearly we do have apple. We search for apple. What do? We return true because apple does exist in the try. So next, let's run search again, and this time, let's check if a word app exists inside of our try. App, right? Not apple. So obviously we know that starting from the root again, we do have a lowercase a, just like we checked. We do have a lowercase p after that, and we do have a second lowercase p. So since we do have all three of these characters, right, A, P, P, shouldn't this function return true? No, we're not returning true, and the reason is this node is the last character of the word, right, P, and it's not marked blue, meaning it's not marked as a word, right? Remember, we only inserted apple into our try, right, into our tree, and we marked this as the end of the word. We never inserted app into the tree, so this is not marked as the end of the word. So we return false for saying that app does not exist in our tree. App is not a word yet. Next, let's run another function on our tree or try. We're going to check, does a word start with app?
This makes sense.
How can we check if a word starts with app? Well, we're basically running the exact same thing what we've done, right? We're starting at the root. We're going to check.
I can't visualize like the struct.
Character by character. So this is pretty, like all three of these functions are pretty similar, right? We're checking character by character for all of them. Start at A,
an array
A
of
exists.
nexts.
Check P, P exists. Check another P,
Right.
P does
Array of
exist.
nexts.
So since
children.
we found all of the characters, right, we're basically guaranteed that either this is a word itself, which clearly it's not, right? We never inserted app, or we're guaranteed that there is some word below that has been marked, right? Because if we inserted these characters, we only did that because we were inserting a word, so there's guaranteed to be at least something that is marked blue down here, right? So once we found this character, the second P, which is all the characters in here, then we can say true, right? There definitely exists a word that starts with app, right? And so this starts with function is the main reason we're even implementing a try in the first place. Because if we want to insert words and search for words exists, right, to check if a word exists, we could just use a hash map for that, right? Because hash maps can, or hash sets can do both of those things in O of one time, right? But this is really the problem. Starts with, it allows us to check prefixes, right? So now let's say we were inserting another word. Let's say we're inserting the word ape, right? APE. How are we going to do that, right? We're inserting another word. What does that mean? Are we going to say APE and then just create a separate node for each of these as children, right? And just connect them such as that, right? This is a child of A. This is the child of P. Are we going to do that? No, because we could reuse it, right? Why would we have duplicate A's in the first position when we already have an A over here? So if we are inserting this word ape, we're going to leverage this A that we already created. Great. And then we're adding the second character, P. We're going to leverage this P that we already created. And so we've inserted the first two characters. What about the last character, the E? Do we have an E over here? No, right? There's no E in the third position. So what are we going to do? We're going to create another child node, right? Now we create an E, and last but not least, we mark that this is the end of a word. So you can see that a try actually has the potential to be pretty efficient because we are reusing a lot of nodes, right? We're not necessarily creating a separate node for every single word. Now, let me just show you one last thing before we jump into the code. So we're going to do one last function. We want to check, does any word start with B? And I'm just illustrating why we're even implementing a try in the first place. It's because the starts with function is very efficient compared to other data structures. So for example, let's say we had a list of words, a list of strings, and let's say the size of that list was equal to 1,000,000, right? How long would it take for us to check if any word starts with B? Worst case, we would have to check every single word in the list and check if it starts with B. And what if there was 0 words that started with B? Then every time we would have to go through that entire list of 1,000,000 words. But with a try like we've implemented right now, it's very efficient. Here you can see we have 2 words, right? We have one word here and we have a second word here. And it's possible we could have 1,000,000 other words, right? Like clearly there's probably a lot of words that start with the character A and maybe so on. But when we run this function starts with B, all we're checking is we're starting at the root. We're checking, do we have any children with the character B, right? We check this first layer. How large is that first layer going to be? Well, we know that there's 26 lowercase letters, right? So worst case, it would be lowercase 26. And that's pretty efficient, right? So when we check, hey, there's a lowercase a, but there's no lowercase b. So for this starts with function, we can return false. And that was done very efficiently, right? 26 is basically big O of 1. So this is a super efficient way to check prefixes, right? And that's why they call this a prefix tree. Prefixes can be checked very efficiently. So now let's actually jump into the code. All 3 of the functions, insert, search, and starts with, are pretty similar functions. So even though we're going to write a lot of code, it's going to be mostly similar. So let's jump into that. So our job is to implement a try, but we can't really do that without implementing a try node. So the first thing I'm going to do is create a try node, and all we're going to do is just create the constructor. So in Python, that's what I'm doing, and net is basically the the constructor, and I'm just going to have a couple of member variables for this. So we are going to have children of a try node, right? It could have children. It could have 26 children, but instead of doing an array, I'm just going to do a hash map because that's easier. And remember, we can also mark every single node as if it was the end of a word. I'm going to say end of word is going to be a variable. Initially, it's going to be false, but we could set it to true if the character was the end of a word. Notice how we're not actually storing the character itself in the try node. That's going to be implicit from the hash map, from this hash map. So if we were adding let's say a character a lowercase character a, we would say to children, we would say children for character a is the key, and we're going to create a new try node for that character a. Right? So that's how we're going to be doing it. That's how we're going to be inserting a node. So that's our entire try node class. Now let's actually get into the try node for that character.
Okay, let's try to do a little bit before I look at his solution. Self.root equals try node. All right. For C in Word. If C not in we can do like cur. Is it like that? Cur dot children. Um Oh wait, I need to do this is the starts with function. This is this is that. It's looking good so far. Nice. W implementation of a try by me.
Character A, right? So that's how we're going to be doing it. That's how we're going to be inserting a node. So that's our entire try node class. Now let's actually get into the try class. So the first thing we're going to do is initialize this. So let's get rid of this comment. And for initializing this, all we're really going to need is a root node, and we can get the rest of the nodes from that root. So we're going to create a root try node, and that's it. That's all we're going to do for the constructor. And once the try node is created, we basically have an empty tree. Even though we have a root, it's empty because it does not have any children. So we technically have not inserted any words yet. But now let's implement the insert word method. For this method, we are going to have to iterate through every single character in the word. So we're going to initialize our self. Current is going to be set to the root, so we're going to initially start
he also did
at
a
the
curve.
root, right? And then we're going to go character by character in the word.
There's kind of no reason for me to watch this. I feel very confident about my implementation.
For this
Let's
work
just quickly
with
skim
those
through
nodes. And the remaining two functions, search and starts with, are actually going to be very similar to this insert function.
I literally, my code is an exact copy of this.
Let's get started on search. So we want to search to determine if a word
Except
exists
he's using
or not.
cur with
so
no
just like the
double
previous
R.
function, we're going to start at the root node, so self.root, and we're going to go character by character in the word, and we're going to check if this character exists in our tree. If it does not, so if C not in current.children, if this character the last, and we're going to go character by character in the prefix this time, right? We're not given a word this time. Return true because we know that there's at least one word that starts with this prefix. We don't have to determine that the prefix itself is a word. So that is the entire code. I can zoom out so you can see the entire thing, and we just have one small typo over here. This is children. And so other than that, this is the entire code.
Nice. Okay, I wanted to quickly look over. You know what I forgot to do, guys? It's really important. I forgot to look at the comments on this problem to see what was going on. What were people saying? Hint, 2 and 3 are erroneously the same. I did not see binary search at all in this problem, dude. Oh, but it's the same thing I did though, kind of. Not really. Like I get it. When you sort the array, you start from the smallest number and then you just do binary search on like if that square exists. I mean, that's cool. Excuse me. But I'm pretty sure binary search and this are the same thing. I guess binary search doesn't use extra memory. So you can make that case, I guess, but I don't think that really matters. It's only 24 comments though. No one's really commenting. All right. Let's get like 20 minutes on this project. 20 minutes is just not a lot of time, but dude, I am so tired. Jesus. don't drink and, don't do any of that. How much is a time travel ticket? 70 Leetcoin. How many Leetcoins? I have 260 Leetcoins. All right. So what do we got currently going on? What did I just... Wait. Yeah, so currently we got the playlist catalog. But an issue is... So, like, these all work on their own. But the problem is that you can play both of these at the same time. So there can only be one... I have no idea how to code that, though. Besides, like, maybe... Yeah, that's gonna be what we're gonna need to figure out here. That's my goal for the next 20 minutes, is to figure out how, when I play this, these all stop. Like, if I go here, it shouldn't be able to do that. How the hell do I do that? Man, this is gonna be tricky. Okay. Do I even need... Yeah, I do. You can never have more than one song playing at once. Like, every time you do song.play, this needs to do something. Man, how the hell do I do this? Do I need like a global function, maybe, possibly? Like here? I feel like that's bad practice, but... Like, pause all songs. Or reset. I'll take like a playlist catalog. Playlist catalog. I don't know if this is the right place to put it. Maybe I should put it in here. I don't know. I can't call it in here, right? I don't. No, I need to call it from here. Oh, I know, not from. Do I need to do it from here? Well, if I know I only have one playlist catalog, maybe I can use that to my advantage. And this should probably not be in here. Public static void reset all songs. For non-static field cannot be referenced from a static public. Is it? Can this be static? Oh, now what? Wait. There you go. Okay. For song SP. What's wrong with this, bro? For each not applicable to type. Why not? Oh, it's P dot. That's the problem. No, that makes sense actually. Do I not have a get playlist thing? No. What am I, stupid? Public playlist get playlist. What's the problem, dog? Oh yeah, oops. Dude, I'm actually tripping so much. I'm actually tripping right now. I'm actually tripping. Not even trolling. I'm literally tripping. Sure. No. Maybe final. No. Probably. All right. There you go. All right. S dot reset. So I think if I go into here, there's got to be a better way to do this, but I'm not really worried about it right now. Okay, let's see if that works. It did work. But now whenever I click the play button, it resets it. Shit. Accept the song. This should take a song thing. Wait, hold on. Yeah, facts. We straight spitting, man. We straight spitting. What am I saying? Ah, man. I love to code. I actually love coding. It's actually my favorite activity. What the? Yeah, okay. Nice, it works. Okay, what do I want to do next? I only have like 5 minutes, so we need a way of making a new playlist. And I just have no idea how to do that. Maybe a search? I can do like, since I just did the try, I can just do like, so the way this program works is that like all the songs are in this folder, and like I can set up like a try to like look up these things, to like to add them to a playlist. Yeah. Okay. So how do I want to do that? I need a song search thing. How do I do that? Song search thing. Is that another class? Probably, dog. Song search. Private VBox layout. Oh man, I still have to study for a midterm, dude. Like it's over for me. What do I want to do here? Public. We can make this constructor really quick here. What does it take? I don't think it takes anything. I need like to do a try in here, so it's like private try. Oh, shit. I think I'm gonna do like this, and then private class try node. And let's just quickly set that up. Let me go to this thing. Let's do public. Public. How do you do dictionaries in Java? I'll ask ChatGPT. How do you do char, bro? How do you do char? It's just character? Character. Sure, dog. Map character person. Oh, it's one trinode to another trinode. Right? And then it's public. Okay, that's all I'm gonna do for now. I don't even know if I'm doing this right, but I really gotta go. It's here for this midterm. All right. Peace.